So, it's a pleasure to introduce the next speaker. He is the only representative of this department. So, but he is talking about a subject closely related to what Eitan was talking before. Already dealing with the limit of n to infinity, right?
Yes, yes. Okay, thanks, Wolfgang. First of all, I would like to thank the organizers to give me the opportunity to give a talk here, and thanks all for coming. So I'm going to talk about, I put up this title of Asymptotic Preserving Schemes on Kinetic Models with Singular Limit. It looks like a little bit a different topic than Eitan's talk, but it's actually very much related. I'm just trying to frame it in a way like which kind of can emphasize some numerical aspect of as you will see. So here's the outline of my talk. It's already dying. Okay. So I'll first try to give an introduction about what is this asymptotic preserving thing, and then I will just focus on one of the examples which is actually related to these swarming models, which Eitan has already given a nice introduction about, and then just trying to talk about some numerical difficulties and how to resolve them. So here is basically what is this asymptotic preserving scheme is about. So let's just consider like there is a system like F is a solution of a PDE or kind of any kind of equation with a parameter, this epsilon here, and then so this guy has a limit when the parameter say goes to 0, for instance, and this F is kind of a solution of the limiting system. So in many cases, both these solutions for these epsilon and this limiting solution F is of great interest. One typical example is about these kinetic equations and the corresponding hydrodynamic limits. So for instance, if you have a Boltzmann's equation, famous Boltzmann equation like this, and then so if you put this Knudsen number here as your parameter here, and when you kind of take this epsilon goes to 0, you can get the compressible Euler limit where these solutions, limiting solution basically converges to so-called Maxwellian. Basically, it's kind of Gaussian distribution with all these parameters, this corresponding to macroscopic quantities, density, velocity, and temperature, and which satisfies, say, these compressible Euler equation. Well, there are other kind of limits, hydrodynamic limits from the Boltzmann equation, say to Navier-Stokes or to incompressible Euler Navier-Stokes, so on and so forth. Basically, as you see that systems like this really both the full kinetic system and the limiting system are of great interest. So in terms of numerics, basically what one can do is to somehow design a numerical schemes on these say Boltzmann equation, for instance, and also very interesting thing is to trying to design the numerical schemes for this limiting equation. So suppose we have something here. So this is kind of a discretization of what kind of approximation of this system, and so these schemes will kind of gives you the approximation of the solution F epsilon, and there is probably another scheme which works for the limiting system. Okay, so these are the schemes, and what we mean by this asymptotic preserving is the following. So basically, it says that this H really doesn't really depends on this epsilon, namely that if I have a scheme here, then the stability condition doesn't really require some epsilon. So no matter how small this epsilon is, my scheme can kind of resolve these things uniformly. So this discretization doesn't really depend on your smallness of your parameter. So in a sense that once you create this kind of scheme for any epsilon, this automatically solves the limiting system as you put this epsilon to be very small. So this is kind of a compatibility. So this is so-called asymptotic preserving schemes. So it is a scheme which kind of can work simultaneously in these regime where epsilon is, say, of order 1, as well as the limiting regime when epsilon approaches 0. Okay, so you do not really have to switch back and forth, but just use it directly. So this kind of asymptotic preserving scheme framework was proposed by Xi Jing in 1999, and there are like a very booming of works which under this framework, and especially for this kinetic equation and this hydrodynamic limit. So I'm not going to go over this for my talk today, but I would like to address one issue here, is about what happens if this limit f of the equation, okay, this is singular. So namely, for instance, if I have a kinetic equation, its solution is basically a density which depends on time, location, and velocity. And one type of limiting behavior is so-called the monokinetic behavior, namely that really at each position there is only just one velocity which is occupied. So if you write this limiting equation out as this, it's going to be a Dirac delta with respect to the velocity. So basically the velocity at this position x is just, there is just one velocity. So this is so-called the monokinetic stage. But then you see that if my limiting system looks like this, then this f is actually singular. Okay, so you have a Dirac mass. So if you think about if you would like to trying to find a discretization or approximation, this things to this singular f, you know that there is going to be some problem because your actual solution here is not smooth. So if you lose smoothness, and then you basically lose accuracy when you try to do approximate. So your target is really bad. Okay. So, and if you want to try to create this asymptotic preserving scheme, basically says that when epsilon is very small, these things will more or less doing in a very harmonic way to recapture this singular limit, this limit. But since this guy is singular, so we can even imagine that if this is an asymptotic preserving scheme, when epsilon is very small, then even this scheme is going to behave really, really bad. Okay, really, really bad, just because of this singularity. So,
can I ask?
Yes.
When I look at this diagram,
yes,
you are talking about convergence. So, in which norm?
Oh, this is a fantastic question. So I'm actually hiding a lot of things. I'm just using these arrows. The convergence. Okay. So basically, there are multiple arrows. That means that multiple convergence. Okay. So the first thing is really this convergence. So basically, you have a PDE here. This is the solution. And you have this limiting solution. So this is nothing about the discrete system. So this convergence is really about you have two systems, like from Boltzmann to Euler, and what type of convergence it is. It's a very, very deep question. It's a very, very deep question. I mean, but it really depends on your equation itself. So this really, to understand this arrow, you really need to analyze what's going on here. So I will give you some examples about what kind of convergence in some case. But in general, it's a very deep question.
But in the example you gave, both equations or both quantities are really convection dominated. objects, right?
No, not necessarily true, as you will see later. So the limiting procedure is not convection dominated.
So this is a diffusive problem.
Again, depends on what type of limit. I'm hiding a lot of details about what type of limit you're getting.
I have even more problems with this conversion.
Exactly. So this is very deep, actually. I'll just give you some more kind of. I'll tell a little bit more for some specific case that I mean in this talk, but in general, this is really something really deep. Not even saying about this level. But you see that to understand these, how these convergence goes is really important in order to really go through this whole diagram. Okay, so but hopefully later I will give you more information about this convergence. Okay, so but now you see that a very the problem is really about this guy is really singular. So if this thing is singular, you can see that this scheme you don't expect too much. Okay. So how are we going to resolve this thing? Well, there is one very simple ways to do it. At least it looks like simple is to do the following. So I start with these solutions of this PDEs or solution of these discrete problems, and I do a transformation. Okay, so suppose I have some transformation which depends on epsilon. So you can think about this as kind of a mapping. And if I map this diagram into another diagram which with this transformation, and then if I'm very lucky to see that, after this transformation, the new limiting profile G is not singular anymore. Then we are in a much better situation. So basically, here, what one can do is just do these asymptotic preserving scheme, which has been really developed in a very nice theories. So you see that as long as I can somehow find a transformation to change these singular problems into a not singular problem, then we are in a much better shape. But you see that basically the singularity is captured in these transformation. So this mapping will become more and more singular as epsilon becomes.
That must be very ill conditioned.
It's very ill conditioned. It's very conditioned, as you see. So, but this is kind of the idea. You're really trying to pay something here, so pay with a very bad transformation, and then what you gain is that afterwards you get a nice system that you can tackle.
So if you settle from the beginning to have a convergence that, say, covers measures, you would be okay, right? Because see, formally even in L1 the convergence would be okay for your singular measure.
Well, okay, it really depends on this. Yeah. So let me just trying to I just trying to say that this is kind of the simple ideas and trying to hopefully just hide the difficulties here into this transformation. And I would like to say that if we have a somehow explicit transformation, so that then these hard problems will become simple problems just by this transformation. Of course, it's very easy to see that as long as you have this transformation, things are going to pretty nice. But the difficulty is how are we going to find this transformation? Right? So where is the recipe comes from? It really comes from the very good understanding about your limiting procedure. So for instance, if this guy is going to approach a Dirac delta, how fast is going to approach this? And this is going to be encoded into this transformation. So that's exactly why we really need to know a lot of information about these PDE level this limiting process, exactly as Wolfgang said, in order to try to create this guy. So, and this is really case-by-case things, because in general this is very hard. For instance, from Boltzmann to to Euler or Navier-Stokes, it's very delicate, and the results are very limited. So, but for today's talk, I will really just trying to concentrate on one concrete example about how this framework can work. And this thing is about these swarming models where Ethan just introduced in the previous lecture. So let me just okay. I only put 2 pictures because I know that Ethan will do videos, and so. But if you just Google swarming or collective dynamics, and you'll find all beautiful videos about these birds and fish. And so to model these things, so there is this 3-zone models from Craig Reynolds, which has already been discussed. Like if you have a relatively long range, and then you get attraction, and a relatively small range, you get repulsion, and the middle range we have alignment. So this is kind of the framework. So so the agent-based model. So here I'm talking about the second-order model as opposed to the first-order models where Ethan talk about for part of his talk. So basically, this second-order model, second order means that you really just you require the dynamics of not only the position but also the velocity. So by this Newton's second law, basically mass times acceleration is equal to the force. So, and this force is kind of an interaction force which definitely will not just depend on itself, but it depends on its neighbors. So, so which makes this dynamics to be kind of a coupled ODE system. And so for the attraction and repulsion, so one can use this attractive repulsive potential, which Ethan mentioned. So basically the force is the minus of the gradient of the potential, right? And for alignment force, well, here we are going to focus on the Cooker-Smell model. So there are another 10 examples, right? So as you already explored it, so we're going to focus on this Cooker-Smell model, which you see that basically the alignment means that my velocity is going to be aligned by your velocity with the weight, which depends on the distance between you and me. Okay, so here for Cooker-Smell it's geometric distance, but it could be more. Okay, it could be more. So and the flocking phenomenon, which Ethan already discussed about in a more general framework. So the long time behavior is really about since emergence of flocks under some suitable long conditions. So what I try to do is to talk about these large crowd dynamics, namely that when the number of agents is becoming large, so as a limit or mean field limits, then one can really obtain these so-called kinetic equations where F is basically the density which depends on the location and the velocity. Okay, and then this is so-called this Vlasov type kinetic equation where this transport term which relates to the x dot is equal to v, and then this term is related to in a particle in a agent-based model the Newton's second law, where this F is the forcing term. So for instance, for Cooker-Smell model, then this force is going to be given by, it's kind of a continuum way, but it's still the essence is the same. My velocity is going to be aligned by your velocity with the rate weight, which depends on the distance between you and me. The attraction repulsion force, again, is the force is the minus the gradient of the potential. So it's basically right into a continuum version of it. So So specifically, if we just talk about alignment, then these models basically is derived by Har and Tedmer. I think Aiton will talk about this tomorrow. So I will kind of very flash through this thing. So basically, this flocking behavior can also be observed just as what the particle level, particle model suggests. So but you see that what we mean by flocking is there are two ingredients. First of all, everybody stays close, so the diameter of this support of things is not like growing forever. So birds are not flying away, say. The second is that there is a velocity alignment. So everybody is going to align its velocity towards they are flying to the same direction. Okay, and just because of this alignment property or flocking property, you see that the long time behavior here is really about velocity concentration. So everybody will really just align. So, and then you see that somehow this limiting system, well, this is just a large time behavior. I haven't talked about any kind of a variable epsilon yet, but you already see that a large time behavior, the limiting profile is going to be something singular. Okay, something singular, like a Dirac delta, because everybody will kind of at the end will flock into the same direction. So you smell some singularity formation here. Okay, so this framework actually can be extended for more models. For attraction repulsion, basically it's the same story. One can actually study the Wilposeness of this system. And it's actually quite hard when you put this kernel as a Newtonian potential. If you put this potential as Newtonian, then this becomes this Vlasov-Poisson equation in plasma physics, and there is a really very rich behaviors which is going on. So global Wilposeness for 3D is studied by Scheffer. And there is a nice non-dot damping phenomenon, which is very important. But so basically, when this is Newtonian, even to understand the Wilposeness of this kinetic system is really complicated. But one can take is that if we have a less singular potential, say this is not like as singular as Newtonian, then things are much easier to handle. There is a kind of a theories to Wilposeness theory for Vlasov type equation, as long as these things are not too singular. So that means that we can really just have a global Wilposeness of this system. If you're just trying to put these two things together, you put attraction, repulsion, alignment all together. As long as this thing is not that singular, then we have a Wilposeness theory. So basically, we know pretty much what's going on for these kinetic system. Okay. So and this is good. This is good. Okay. So starting from this kinetic theory, kinetic system, there are multiple hydrodynamic limits, just because the kinetic system is so huge, and one trying to further simplify or reduce this system into some macroscopic fluid system. So this has something to do with these fluid limits. So what one can do is that we start with these things and trying to calculate the moments. So what you can do is you start with this and say if you integrate this kinetic equation with respect to the velocity variable, and then you got this density dynamics, where density is really just the velocity, the integral of this f in v. And if you integrate the first moment, this will give you the momentum equation here, where this here is the pressure term, which actually depends on the second moment of this f. So if you do it, then you will see, okay, what is the dynamics of the pressure, and then it would has something to do with the third moment, and then you trace the third moment, and it has something to do with fourth moment. So there is a kind of full hierarchy of things going on, and in order to make sense of things, you have to cut it off at some point, right? So one way to do it is really just impose a closure on the pressure. So close it as this kind of a dynamic. So to close this, one can kind of impose some ansatz, so-called ansatz. Namely that if I treat this F as a Gaussian distribution or Maxwellian, then you plug it into the pressure, and you see that basically this, you plug it in and you'll get these so-called isothermal ansatz, namely that the pressure is really just proportional to the density, so that you have a closed systems to study. And rigorously, one can really just trying to cook up a term here, and then doing some rigorous analysis, and then trying to get into this limit, and this by Copper, Millet, and Trevisa. I'm not going to get into the details for this. Also, one can deal with, say, if we have a monokinetic ansatz, namely that this F looks like a Dirac in V, and you plug it into this pressure, and the pressure is just gone because these two things are the same here. So, and then this will gives us this pressureless equation, so there is no pressure. Okay. So this macroscopic system has been studied intensively for the previous several years, and I think Eitan is going to talk about more on that. But I'm going to just trying to focus on one different type of hydrodynamic limits, which is so-called the zero inertia limit. Yes.
So is it depending on how you close the pressure, whether you get viscosity?
Oh, that's actually a very good question. So yes, so this viscosity can be kind of derived if you try to kind of look on some more kind of if you start with an expansion, and then if you have some higher order terms, and this some of this is corresponds to the pressure. So the calculation, even in the formal level, it's really messy. Yes, like for instance, from Boltzmann to Navier-Stokes, you really just trying to do the formal calculation, and then it just depends on how you really just trying to cook up this ansatz. It will reflect the viscosity will show up as I mean, as a matter of fact. But I don't want to get into the details because it's really something kind of too deep. It deserves a course, I mean, all by itself. So, but I would like to focus on the zero inertia limit. Basically, so this is the total mass, which here is becomes very small. So this is so-called zero inertia. So you kind of perturb it from nothing is there, and then if there is a little bit things here, then what's going on? So now epsilon, our parameter appears. Okay, here our parameter appears here. So it more or less like a kind of a Boltzmann-like equation. It's not really Boltzmann, but you see that what happens here, the interaction force is really is really depends on what kind of forcing you're putting there. So we are going to mainly concerned about two systems. So one is about the attraction, repulsion, and so-called relaxation. So relaxation is just to relax these velocity variable minus v here. So just remind you that the attraction repulsion is just given by this minus gradient of the potential. And also the next, I put this here just for a reason that you'll see in a minute, but this relaxation is really not really that physical. So, but the second case is more realistic, you have attraction, repulsion, and alignment. So this is exactly the three-zone model that I described at the beginning. So and for the alignment, we use the Cooker-Smell alignment for this talk. So we're just trying to see that what's going on with these things when epsilon approaches 0. So let's just first try to understand this limiting process of this equation from f epsilon to f, without talking about the numerics yet, okay? The discretization yet. So what can we know? So let's just do a very kind of formal calculation, namely, I think formal means informal in this in this gas dynamics community. So what do you do? Well, if you formally say that set epsilon goes to 0, namely that what the term which is dominated is here. So you see that basically the transport is not there anymore. So in the limit, it's really not the transport dominated case. When epsilon goes to 0, in this case. So this is equal to 0, and then what we can do, you multiply a test function, and this any kind of test function, and this still gives you 0 in a very formal level. So and you're free to pick this test function. The first function you pick is then you can integrate by parts, because we assume all the smoothness. So if you integrate by parts to differentiate in this guy, then when you take this function, these things to be 1, test function to be 1, you basically get 0 is equal to 0. You get nothing from the highest order term, but so from the order 1 term, if you integrate this is gone. So you get basically the continuity equation here just by integrate this guy with respect to v. Okay, very formal. But if you try to pick these guys to be v, this test function to be v, then you basically this says that the integral. So this is going to be 1, and not 1. A vector 1. So that means that these things are going to be 0. Okay, if you plug it in. If you plug it in for these two systems, you'll see that for the attraction, repulsion, and relaxation, you'll basically get the velocity will looks like the minus of the gradient of this guy. So this corresponds to relaxation. This corresponds to attraction, repulsion. So this is it. If we put alignment instead, then of course it has something to do with alignment. Here is in replace of this. This relaxation in velocity. So this is what the dynamics looks like, right? And then one can also do. How about let's do the second? So we take the test function as the second moment. Actually, if we use this subtract this u to make it to be a second variation, then after just plug it in and do the calculation, you'll see at the end you'll basically get this second variation is equal to 0, and this is exactly corresponds to these Dirac delta, because your variation becomes 0, namely that your velocity is concentrated. So you see that in the limit, what is the limit, formal limit of this procedure? You'll see that what happens is that your limit function will looks like some density function depends on x, but the velocity is really concentrated at the point. Okay, so and this is exactly the monokinetic singular thing. And what is rho? Rho satisfies this continuity equation, and what is u? Well, u satisfies this thing. Okay, so this is kind of a formal derivation to see that what exactly is the limiting process. Of course, everything is formal, so it doesn't really answer the question of Wolfgang's what really the limit is. But this actually has been studied, in particular for the aggregation repulsion with relaxation. This limiting system, if you remember, this is the u. So if you pull it in, this is exactly the so-called aggregation equation, which has to be studied by. It's relatively well studied, and And what really, okay, now here's about this limit. So what is this limit? So there is a regular passage to the limit from the epsilon towards this aggregation equation. And well, now for this setup, the limit is in a very weak sense. It's weak star immeasurable. So very, very weak sense, which is really bad for sure. But you see that this actually gives us a very nice aggregation equation, which has been studied by a lot. But the problem is that, so here is something about modeling, because this is about the workshop is about. So this relaxation is really not just come from nowhere. You're just trying to make an extra term so that it end up with a very nice equation that people can get your hands on. But instead, if we try to change this relaxation into the alignment, which is much more realistic, right? So then what happens? Well, of course, as you see from the last page, you basically have these things which determines your velocity, and this is kind of very ugly-looking, complicated, implicit definition of the velocity field, and it's nonlinear and non-local in general. So what happens with this system? Well, this system kind of serves as a more realistic system than the aggregation equation, just because the alignment is more natural. But now you see that what happens for the ill-postedness of this system. Immediately you see that this system is ill-posed. In the following sense, for instance, you see, given a rho, what can we do? We have a uniqueness on the velocity field? The answer is no, because if u is a solution, then if you add a constant, these two cancel. So this is another solution. You lose uniqueness, and you don't have ill-postedness. So which is super bad. So if our limiting system is even ill-posed, then forget about doing anything about that. But how are we going to rescue? Well, here is what can be done. So there is additional restrictions or conditions which is true for the kinetic equation, which is the momentum conservation. And this is something that one can be used to save the day. So
it's like a weak initial condition.
It's kind of like if you kind of trying to enforce this momentum conservation, at least you see that adding a constant on top of this u is going to be eliminated, because adding any constant you basically violated this restriction. Okay, and the good news is that with this restriction we actually can prove the global ill-postedness of this system. Okay, global ill-postedness of this system, and this is a joint work with Federico and Son.
Ill-posed, you mean there exists a unique solution?
Yes, there exists a unique solution.
But nothing about stability and things like that.
Actually, you can show that the velocity field is Lipschitz. If your velocity field is Lipschitz, you have everything. You have everything, stability or so, because it's a continuity equation. So if your velocity field is Lipschitz, and you get everything you want. Okay, so of course this really depends on these two kernels. I really need these two kernels to be good enough in order to. So
the kernels really do the smoothing, because.
Yeah, the kernel cannot be, say, Newtonian. If this is Newtonian, then I think it's a little bit too much. But anything less than Newtonian is going to be fine. So for this one. So yeah, I mean, but then you basically, this is just to tell you that the limiting system has some kind of regularity or has some kind of ill-postedness. So, and well, in the same paper we actually proved this regular passage to the limit from the epsilon to this limiting system, and the convergence is still very weak, the same weak starring in measure. Okay. So this is the understanding about the bottom line of this framework, which is very important. So now let's just talk about how are we going to deal with this discretization, and how things can be done in a asymptotic preserving ways. Okay, and this is so-called this velocity scaling method. So this is a framework. So basically, as we see that we have a limiting system where this limit has this kind of velocity concentration, so which is exactly the singular things that we were discussing about. So if this guy is singular, then what can we do for the transformation? Since the bad things happens for this velocity, right? So if velocity is going to concentrate as epsilon goes too small, then what we would like to say that, you're getting more and more and more concentrate, that's fine. My rescaling is going to scale it back, right? You just provide this, this is a L1 preserving scale, right? This is usually how you approximate identity, basically, right? But then you see that what really matters. So you see that first of all, we are going to kind of trying to find which point we're going to go to concentrate on, and then how much we are going to rescale these things in order to hopefully make this quantity after rescaling to be nice. Of course, we have to define what do we mean by nice, but at least it's not like a Dirac delta. Okay, so if things are getting concentrated, we are just trying to push it back and scale it back to make things done. Okay, so the shift is usually just you just shift it towards its center, so the averaging point. But then this scaling is more really, it depends on what the behavior of the system exactly look like. So there's really, the goal is trying to choose this the scaling factor really appropriately, so that after you the scale, this guy becomes non-singular. That is the real goal about that, right? So how are we going to choose this guy? Okay, the scaling factor. So briefly talking about this velocity scaling, this has been actually applied to many systems where you have this singular equilibrium as time approaches infinity. So this framework. And of course, in this case, then this scaling factor will really depend on the time. So when time becomes larger, you get more and more singular. So how are we going to think about how are we going to choose this? Well, so it has been studied for different models, like a linear Fokker-Planck. Well, this thing is not really drives things to be singular, but it could be near singular. And also the granular gas case is really things are going to drive into singular. So the idea is really they just pick the omega as a square root of the temperature. The idea is that if you think about your profile, it's just a Gaussian, right? So if you want to try to rescale a Gaussian into a normal Gaussian, what you pay? You pay just the square root of the temperature, okay, which is just standard deviation. So, and then you scale it into the Gaussian, standard Gaussian, okay. But of course, this only works when your profile actually looks like a Gaussian. Okay, so it's kind of very close to the equilibrium, and hopefully the equilibrium is the Gaussian. Well, it's the case for Fokker-Planck, not really the case for granular gas. So what we are actually doing, this is with a joint work with Thomas Ray, and we're just trying to propose a new way to somehow to learn this scaling. In a better way, not just to do a naive square root of the temperature, but trying to get a better estimate on this omega, and in a more dynamical way. So you learn it from the dynamics, and it's much better than this general approach for the system that I just explained it to you, and in a sense that it is actually exact for a so-called spatially homogeneous system. Let me quickly talk about what's going on. This spatial homogeneous system means that I just ignore these transport term. Okay, so if there is no transport term, and this is the dynamics, and then if you insert these, you do the transformation, and you get into this bunch of things just by hand calculation, and this whole things. Let me just try to say that in this case, actually, if you calculate these this velocity actually, the velocity just satisfies this equation, which cancels out this term. So this is the contribution from the velocity field. And then how about this field here? You'll see that basically if I manage to make this omega such that this term vanishes, then what we have is that this rescaled function, the time derivative of this rescaled function is just 0. So basically, after your rescaling, your profile not even move. So this is perfect because you exactly captures the correct scaling at each point at every time. So this is very ideal. You cannot do anything better than that because this is just the exact thing. So, and to make sure that this guy is 0, basically this is the things that you're going to use. Okay, so and it depends on these script A, which also this guy might depends on density and velocity. So somehow you are just pulling out these your information about the macroscopic quantities into to determine these scaling factor dynamically. Okay, dynamically. So which is quite nice, but well, if you have a transport term, it destroys everything. That's the fact. I mean, even for Boltzmann, and this is known as a main issue. So if you do the same thing and you see that this is going to be very bad looking, well, it's really bad looking just because the following. So if you just write it down in this way, and then you cannot really expect this exact scaling just like before. The reason is the following. So first of all, this term, you cannot really just cancel it out, just because this is if you calculate the dynamics of U, and then there is this kind of a pressure terms appears. We have no closure yet, so this pressure terms really just appears here, which is kind of bad. If you insert this chunk into this thing, it does not cancel out, but rather there are some terms which remains. Also, for the scaling factor, you see this scaling factor. Now, if you would like to make these guys to completely vanish, you cannot, because there is a new scaled variable here, so which can vary. So there is no way like you can make it completely disappear. So, well, the best you can do is that you leave it as it is, and trying to make the others just vanishes. So this is what we can propose to the dynamics of the scaling factor. So if you insert all these two recipes in here, and you will get something like this. Unfortunately, the right-hand side is not 0, but it looks like crazy. Okay, but I claim that this is much better than the original case of f epsilon towards f, because we will kind of trying to say that with this kind of g epsilon, the limit when epsilon goes to 0, this limiting profile is nice. It's nice, and this is our goal. Still remember that we're just trying to change a singular limit into a regular limit using this transformation. So here is the transformation, and I'm just trying to convince you that after the transformation, even if this thing looks ugly, it's going to give you something really nice. Okay, so so back into this framework, and I already presented to you what kind of transformation we will have, and the idea is just to say that as long as this guy looks good, then we'll basically just trying to apply whatever asymptotic preserving scheme on the right-hand side, without worrying about the singularity. Okay, without worrying about the singularity. So. So how are we going to make sure that this guy is not really is good? Actually, it's hard. It's very hard, and this is really related to the Wolfgang's question before about how these this limit is going. I think how this limit is going. It's going to be because this limit is really weak, so there is some trouble. Okay, so basically we call the, so what do we mean by G is good? We give a criterion of what do we mean by G is good. So if you think about if I do this kind of scaling, start with the Gaussian, if I scale too much, they are getting concentrated. Okay, if I scales too little, then it gets spread out. So a good quantity to criterion for a non-singular is to say that it's not growing too much, right? It's not spread too much. So then we're happy, okay? So this is kind of the criterion to get a non-singular profile, and we're just trying to check if our transformation is going to really make the solutions to be non-singular, okay? And if you recall this crazy dynamics here, what really matters, the difficulty is really about these controlled spatial derivatives here, because things can be really oscillatory. Okay, and this is really bad. So to see this, you can, as an example, let's talk about the dynamics of view, and this is the dynamics of view. And here, this is the pressure, which appears here. And if there is no pressure, actually this corresponds to the macroscopic second order hydrodynamic system, which I think Aiton will talk about tomorrow. And basically, the velocity is actually getting controlled if our initial condition is good enough. Okay, so which is nice. So if there is no pressure, then things are fine. On the other hand, even if we have pressure, but our limiting system is nice. I mean, just as I explained, that the limiting system, you really have a very nice Lipschitz regularities on this thing. But these two together doesn't really mean that this quantity is nicely bounded just because the convergence is really weak. It does not exclude the fact that things can converge in a very oscillatory fashion. So you basically lose the uniform bond, and this is super bad. This is actually, I think it's a very big problem in general for these hydrodynamic limits for all gas dynamics problems. So it's kind of some deep things which is very hard to avoid. So so we kind of step back a little bit and to say that if we cannot prove it, we assume it, right? This is so we're going to talk about these non-oscillatory assumptions, and if somehow this kind of oscillations can be somehow bounded, then if a priori we have this bound, then I claim that everything is going to be fine. Okay? And basically it says that as long as you have these non-oscillatory conditions, I can guarantee you that your limiting profile after this transformation is nice. Nice in the way that I already explained it to you. Okay, once this is nice, we are really happy because we do not need to worry about these scaling things anymore. So some remarks. Okay, one remarks is that even if these conditions, we cannot really show it a priori, but the discrete version of these conditions can be tracked using a numerical scheme. So basically, you can when you push the numerical schemes, you can keep an eye on this quantity. As long as this thing is not driving you mad, then you know that you are in a very good condition. Okay, so this is kind of a step back approach. Actually, the good news is that in many kind of physically relevant initial configuration, if you revolve this system, you don't have these crazy oscillations actually forming. So even if we cannot really exclude that, probably it actually happens in a very, if you try to to cook up some very unphysical problems. Probably it will happen, but it doesn't really happen in a good form. So once we agree that this guy is non-singular, then we're just trying to propagate these three things: the G, the rescaled quantity, the rescaled profile, and this U and omega is really about the shifting and the scaling. So this U and omega really tells you what kind of transformation you're having. So we will put it together, and knowing that the G is regular, so it's much easier to use asymptotic preserving schemes on top of it. So the U dynamics here, well, you see that the stiff term is here, and also for omega there is a stiff term here. But both stiff terms are linear here, so which is very nice. So you use some implicit schemes in order to capture the stiffness, and then you can basically get a asymptotic preserving. If you have an implicit, because there is no self conditions for implicit schemes, so basically your discretization doesn't really it depends on this how big the epsilon is. So this is nicely captured. And for this G dynamics, again, this looks horrible, but you see there is no explicit dependence on epsilon. So so basically you don't have a stiff term here, even if it looks horribly bad. But you can write these things into a divergence form, and you can use the finite volume, or you can put it into higher order terms, and I'm not going to talk about this, but this is how one can solve this issue. And knowing that the limit is not singular, this is actually going to be much easier to get what you want. So okay, so very quickly about some numerical experiments. So this is kind of a validation of the non-assortative assumptions. So these assumptions actually, for giving some initial data here, and you can actually see that they're not really getting bad. I mean, in the long run. So they're actually satisfied.
How do you know that your numerical scheme doesn't have numerical dissipation?
That's a very good question. It depends. So it's related to the other arrow when h goes to 0, which requires a lot more sophisticated investigation, and it depends on the numerical scheme that you used. We really did not get into too much details about that, but rather just perform some numerical evidence to see that actually things are going in a very in a good way, because our really emphasis is how to resolve this singular limit. So yeah, but you're right. I mean, it could be more complicated, and it's method dependent. Depends on what approximation you use. Yes. So there is consistency test. This is for say the region when epsilon is equal to 1. So it's a kinetic region. So your transport is really doing a big have a big role. And then you see that basically when time is not very large, and these two pictures actually somehow, these are macroscopic quantities align it very well by the I norm. We also have some numerical result of that from I think the L2 norm as well. I did not just show you, and also you see that this G, and if you really just use the standard method, whatever standard method it is, this is what you get, and this is for the this rescaled method, and you see that actually they match it very well. But you can imagine as epsilon becomes small or t becomes large, this thing is going to be more and more and more and more concentrated. And without using this scaling method, you don't see anything. You just see, boom, there is a jump, done. But if you rescale, you see all the textures and how things are changing. And finally, this is an asymptotic preserving test. Basically, just say that when epsilon goes to 0, you're really just converging into the limiting system. And there is applications when you use this Morse potential, which was mentioned in Ethan's talk. And for aggregation equation, you really have Okay, so this is for epsilon equal to 1. You get a kinetic region. You get this kind of result. But in a limiting case, this is really convergent to the steady state of the aggregation equation, which for Morse potential, it is just this kind of plateau type of things. And you see that it actually really converges in a very, very, very nice way. And here you have aggregation here, and you have alignment in the velocity variable when epsilon is becoming smaller and smaller and smaller.
So the small epsilon case is actually easier for you.
Yeah, yes and no. So as long as this non-oscillatory condition is not violated, then it's actually much easier. So this, but you see that if you have if you're in a situation that's at some location you're in this region and somewhere else you're in that region, and then you do not need to really just like switch back and forth with your method, but you could just throw it into one of them and you let it run and you get what you want. So let me just try to conclude here. So this is kind of the asymptotic preserving schemes that I presented to you. In terms of when this limiting profile is very singular, what one can do is trying to cook up a nice transformation so that hopefully after the transformation you don't have such singularity anymore. And as you have already said, that in order to cook up a good transformation here, you really need a lot of things. You need to know how these limits how these limits look like, what is the behavior of these solutions, and how are you going to approximate it. This thing. So a lot of information from this diagram is very much needed in order to cook up this thing. And so basically this can be extended into some, say there is if the alignment is singular, then kind of trying to this framework can still work to some extent. And also this system can be this idea can be also applied to, say, Boltzmann or granular gas, but it is more subtle. And finally, I just put the word data here because there is this is another half of the focus of this schools. Actually, all these things, as Eitan already mentioned, this type of collective dynamics, or really, I mean, how to cooperate these things with the real data input, and this is also something very, very interesting. And there are already some works has been done in this direction. So, with that, I think I will stop here, and thanks for your attention.
Thank you very much, John. Any immediate questions? I have one. So, would it be reasonable to do something different? Because, I mean, as nice as this asymptotic preserving thing is, it depends on something very critical, which you may not have all the time. Would you know a way of regularizing your problem from the beginning on the infinite dimensional level so that you can control the behavior when that regularization goes to zero, and then do the discretization independent of that regularization first to the degree that you resolve at the level of that regularization and then bootstrap? Would that be a viable way to do?
Well, I think my answer is yes and no. It just depends on what you're asking. So here, if we already said that I already gives you this part of the diagram. Say I have a system, say Boltzmann here, I have an Euler here, which is given. So you have less chance to try to do some regularization because this is fixed, and then this limit is bad to begin with. So and then you say, I'm going to cook up a asymptotic preserving a scheme or somehow do some regularization. You cannot really bypass this kind of bad behavior to begin with. But if you're just talking about, say, if I have a system and then I'm just trying to create some system which is some kind of a perturbation towards it, if you have the freedom to choose what epsilon it is, I think you're absolutely right. You're just trying to.
Yeah, because I'm thinking in terms of, suppose you aim at convergence in L1. So as long as this is not a measure, like in your limiting case, but as long as you are sort of in a regularized version, you have a real support.
Yeah,
You can use an adaptive method to resolve that for the given epsilon.
exactly. I mean, this velocity scaling is somehow like adaptive because you're really just trying to rescale everything.
But
like
without going through an explicit
explicit
transformation.
Yeah, but I think that if this is not given, then if you can cook up this, then you can cook up this in a good way. I think they even do this. I think Aiton knows this very well about these this velocity average, in the sense that you start with a microscopic system and then you somehow cook up some kinetic system, and then in order to and a good kinetic system so that you can really use it to gain a little bit more regularity. This is actually not even for numerics, but even for the analytical point of view, it's very it's very useful. So yeah, it just really depends on if you're already given both these things with a very bad convergence, or you're free to choose this family of system, and you can make it good, and then trying to use a better schemes in order to resolve it.
If there is no additional comment, I think we have earned the lunch break.
Thank you.
It's going to happen in the